Okay, continuing with quantitative chemistry and looking at stoichiometry, looking at the calculations and chemical formulas and equations. And these notes are taken from Brown and LeMay, edited slightly. All right. First off, chemical equations are balanced and written to really describe what is going on in a reaction. And they always follow the law of conservation of mass, which really states nothing is created. Okay, so matter, an easier way of saying this is matter is neither created nor destroyed in ordinary chemical reactions. So the amount of mass and really the atoms and the types of atoms of your reactants have to equal the number and type of atoms in the products. Okay, so chemical equations. Again, concise representation of chemical reactions. If you notice here, really what's going on is just the atoms are being rearranged from the reactants to form new products. And this is a chemical reaction. Physical changes are just, the atoms stay arranged in the same way. So the molecule is the same before and after of a physical change, whereas in a chemical change, the atoms are rearranged into new compounds. And a picture like this, I think, illustrates that. Okay, balancing equations. Again, the number of type. Remember that the only thing you can change is the coefficients, these numbers. You cannot change the subscripts. These must stay the same. Remember, if there's not one written, it is assumed to be a 1, or it is a 1. But you cannot change the actual compound, because when I combust methane, which is CH4, in oxygen, I form water and, this is carbon dioxide and water. All right, that's describing what actually happens, what the compounds are in the starting and what they end up with as products. Okay, and you don't change those because that describes what happens. Okay, reactants on the left, products on the right, states. We will get better as time goes on in knowing the states. Most often with a organic compound, that is something that has carbons, hydrogens, and oxygens, and sometimes other elements. Most often you'll be told what it is. You should know that at room temperature oxygen is a gas, carbon dioxide is a gas. The result of a combustion, typically water, is given off as steam. Okay, gas. Okay. Coefficients to balance it. Subscripts versus coefficients, you should be well aware of those. Okay, let's talk about reaction types. Being able to classify a reaction into a type lets you better predict what the product is, okay? So knowing the type of reaction, that says type, oh dear. You can predict the products. Okay, and that's one reason to know the type, because for simple reactions, you should be able to predict what's going to happen. First one, and we'll get into this more, is known as a exchange reaction, commonly referred to as a double replacement reaction. Right, and typically these are ionic compounds. Hopefully you can recognize these as ionic compounds. I have silver nitrate in solution and potassium chloride in solution. So in reality, if I were to draw a picture of what is in the solution, okay, I'm going to have silver ions, nitrate ions, potassium ions, and chloride ions in solution. Knowing your solubility rules, this silver ion, when it collides with the chloride ion, is going to form the precipitate silver chloride, which is a solid. Potassium is an alkali metal that's always soluble. Nitrates are always soluble, so that is just going to stay as ions in solution. Okay, so a double replacement is really taking the cation from one ionic compound with the anion from the other, putting it together into a legitimate ionic compound formula. In this case, silver was +1, chloride was -1, so it's just AgCl. And knowing whether or not that makes a solid, a liquid, or a gas. Okay. Remember, let me erase this, things like, knowing that H2CO3, if that's formed in an aqueous, okay, that it further decomposes into water, that's an L, and CO2 gas. Knowing that H2O is a liquid when it's formed, that H2S is a gas. These are all rules from PD Chem. And H2SO3 further decomposes into water and SO2. Okay, so those exceptions making gases, SO2 and water, the hydrogen carbonate further decomposing, forming a liquid, or forming a gas are all things that are called driving forces and make a double replacement happen. And again, we'll go into more detail in a little bit. The second type of reaction is called a single displacement reaction. Okay, and this has to do with transferring of electrons, and we'll get into this in a little bit more detail shortly as well, but just as an overview. Here I have a single element. Here I have an ionic compound. Remember, all metals are likely to form cations. So really what happens is this copper replaces this silver. Silver goes into solution as an ion. And this copper kind of forms the solution copper nitrate. This formula is a little bit incorrect in that it should look like that. Okay, it should be copper 2 nitrate. All right, so single replacement. So this single element bumps out typically the metal in the ionic compound, leaving a single element and the ionic compound. For a double replacement reaction, okay, everybody kind of switches partners. In a single replacement, okay, it's just that single element, hence single element, single displacement. Okay, moving on, combination reactions. In this type of reaction, what you look for is 2 or more reactants to come together to form a product. Now, remember, when we're looking at these, we're really going to be not given the products. You're going to be asked to predict. So when you look at this and I see, okay, there is a element and an element, the only thing really, they can't replace something in the other compound. The only thing really for them to do is to come together. This would be a bit harder to predict, and we really won't look at this kind of reaction until we get into the organic. But you should be able to identify if I have an element and an element that they're going to come together to form a compound. Opposite of synthesis, or what do I call them? Synthesis or combination reactions is a decomposition. How to identify these? If you look, what do you notice is the same in each one of these reactants? It is just a single reactant. There's nothing for it to react with, so it is going to decompose into either elements or compounds. There are things that you need to just know that they do this. One is if calcium carbonate decomposes into the calcium oxide and the carbon dioxide, potassium chlorate decomposes to potassium chloride and oxygen. Those are things that you just have to know. typically, in more straightforward decompositions, you have a compound just decomposing into its elements. And again, you do need to know those diatomic elements and what the state of matter they are. Combustion reactions. These are generally rapid reactions that happen in a flame. Most often these involve hydrocarbons and they react with the oxygen in the air. So to identify combustion reactions, you're going to really just look for oxygen as being one of the reactants. When I have a other reactant as carbon and hydrogen, you need to just memorize that they form carbon dioxide and water, and then balance it as needed. And those are the 5 types of reactants, or I'm sorry, reactions. Okay, 5 types of reactants. Double replacement, single replacement, synthesis or composition, decomposition, and combustion reactions. Okay. All right, formula weights. I'm going to go through this really quickly because you should know this. A formula weight is the sum of the atomic weights of the atoms in a chemical formula. So if you're asked for the formula weight of calcium chloride, remember that you take 1 calcium and 2 chlorides to get a total 111.1 AMU. Now, formula weights are generally reported for ionic compounds. It's either atomic mass units, which use the carbon 12 isotope as a reference. Okay. If you are looking for molar mass, it is the same number, but it is in grams per mole. Okay, so we're used to using molar mass because that's what we would be able to use in a lab. Atomic mass units are very, very small because it's basically the mass of 1 atom of calcium chloride. Molecular weight is the sum of the atomic weights of atoms in a molecule. Right? So formula weight and molecular weight is really the difference between an ionic compound and a molecular compound. To be honest, most people get a little sloppy and refer to all of it really as just the molecular weight. Now, it's important though to review this because some of the other topics that we're going to talk about is going to use that idea of the formula weight or the molecular weight. And one of those is the percent composition. You will be asked to calculate the percent composition for different compounds. And what you do is for every element in that compound, you find the percentage of the mass of that element in that compound. So for each element in the compound, you're going to do the number of atoms times the atomic weight of that element over the formula weight of the compound times 100%. I think it's easier if we look at this in practice. So if we look at the percentage of carbon in ethane, first thing we need to do is know that ethane is C2H6. Okay. So if you calculate the molecular weight of ethane, you would come up with 30 atomic mass units. For the percent of carbon, since I have 2 atoms of carbon, each carbon is 12 atomic mass units. So I will get 24 over 30 times 100 gives me 80% carbon in the compound, which would mean that 20% is hydrogen. I think that'll end this, and we will come back and start talking about moles.